lecture for today, we're going to do a quick example for how to do this in R, and then you'll try it yourself. And so let's go back to our baseball example that we started with at the beginning of this lecture series. So what you're going to do here with this data is your first step is to randomly divide the data in half. And so we're going to do that initial split so that we've got 132 training observations, 131 testing observations. So I'm taking my data called baseball. I'm using initial split. I'm setting the proportion at 0.5. Don't forget to set your seed before all of this. That's always good practice to make sure you get the same answer every time you run your report. And then I'm pulling out the training data here. So this training data, this baseball train, is going to consist of 132 observations. And if I pull out my testing data, it would have 131. The second step is going to be to create the cross-validation object. In this case, I'm going to do six-fold cross-validation. I'm picking 6 just because 132 is divisible by 6, and so that is going to give me an even split in each of my groups. So I've got this object baseball underscore CV that indicates my v-fold cross-validation. My third step is going to be to create a model specification that tunes based on complexity, alpha. So let's take just a second to walk through this. I'm calling this model tree spec. This should look kind of like, when we were making our model specifications, for example, for ridge and lasso, we were using the linear underscore reg function. But now we're doing decision trees, and so I'm going to use the decision underscore tree function. And there are a number of different parameters for this function. You can see all of them in R if in your console after loading the tidy models package. If you run !decision tree, it should pull up a help file that can tell you what all of the different potential parameters are. But for this, I'm going to set cost complexity, and so that's my alpha parameter. And I'm going to set that equal to tune because I'd like to tune that using cross-validation. And then I can set my tree depth. And so this is basically going to be stopping criteria for my big tree, that T0 or T0 that we talked about in the last lecture. And I'm setting that depth to be 10. And so that's basically my maximum tree is going to have a depth of 10. And then finally, I want to set my mode to be regression. And so because decision trees can either be used for regression or classification, you want to make sure to specify the mode that you're intending to be fit. And so for this, because we have a continuous variable as my y variable or my outcome, I'm predicting salary, I would like for this to be regression. And then finally, we need to set the engine. And so here I'm going to set the engine to rpart. And that's because the rpart package, that's the name of the package that does these decision trees. And so like we set our engine previously to glmnet when we were doing ridge and lasso, or to lm when we were fitting just a simple linear model, here we're going to set the engine to rpart. If you're doing this on your own computer and you are installing packages along the way, you're going to want to make sure to install the rpart package as well. If you're doing this in RStudio Cloud, that should already be installed for you. So looking at this, what is the tree depth for my large tree? That's right, it's 10. Okay, so now I need to fit the model on the cross-validation set. So this should look pretty familiar as what we've been doing so far when we've been tuning parameters. So first I'm going to create a grid using the cost complexity variable. So basically that's the thing that I'm tuning on. Then I'm going to use the tune grid function and specify my model specification that I just wrote out. I've decided that I'd like to add some extra variables here, and so now I'm going to be trying to model salary. I'm predicting salary based on these variables: hits, years, putouts, RBIs, walks, and runs. I specify my grid, and then I specify my resamples, which in this case is the baseball underscore CV function object. That's that six-fold cross-validation. So looking at this, what alphas am I trying here? What alphas am I searching across? So from this right here, I can see that I'm looking at alphas from 0.01 to 0.05 sequenced by 0.01. So I'm going to look at 0.01, 0.02, 0.03, 0.04, and 0.05. This is something that's kind of tricky to figure out exactly what you want to do in terms of picking the alphas that you'd like to look at. They can be any positive number. And so I did some tweaking here to get it to these ones. But basically, my method is I look first at a broad range of alphas. And if it looks like I can narrow my search, so for example, if it looks like most of the ones above a certain number are kind of all getting the same answer, but there's some nuance kind of at where the minimum is, I might zoom in more. So for example, I may have sequenced from 0.1, I may have gone all the way up to like 100, let's say. And everything above 0.5 looked like it was getting really similar root mean square error. And so I narrowed down to look between just 0.1 and 1. And then maybe I zoomed in even farther and even farther and even farther until I found this region where I felt like I was kind of trying to find a good search within. So now that I've done this, I'm going to choose an alpha that's going to minimize my root mean squared error. And so this is the same code that we used in the last lab where you collected your metrics from the model, you filtered based on the root mean squared error, and we arranged by mean. So we end up with the smallest root mean squared error here, 391, and that corresponds to an alpha of 0.03. There's actually an easier way to do this using tidy models. There's a function called select best. And so instead of having to do these 3 lines, you can just pipe your model into the select best. And if you tell it what metric to use, it'll pick the best value. And so in this case, it's going to pick the cost complexity that's associated with the best root mean squared error. And so it picked 0.03 for us. And so I can take that, I can run my select best, and I can pipe that into a pull, which is going to pull out that value so that it's just the single value in R. And I'm going to save that as final complexity. And the reason I'm doing that is so I can easily plug that into a final model. So that way, if I changed up the different alpha values that I was trying, I wouldn't have hard-coded in an alpha value into my final model. I can just plug this one in. So the final step is going to be to fit that final model. And so I'm going to fit that decision tree specification. I'm setting the cost complexity to that final complexity that I pulled out using the select best function. I'm leaving my tree depth the same, my mode the same, and my engine the same. And now I can just do a normal fit on all of the train data using that final spec. And so this is what that tree looks like. I've got 1, 2, 3, 4 internal nodes, and I have 1, 2, 3, 4, 5 terminal nodes. And so my first node splits on the number of hits, and so it looks at if you have less than 123 hits, you end up over here. If you have more, you end up over here. And then among those with less than 123 hits, those with less than 6.5 years in the major leagues end up with this salary. So that's 36% of my data have a salary, an average salary of $256,000. 25% end up over here, so this is people that have less than 123 hits in the past year, but more than 6.5 years in the major leagues. They end up with a salary of $500 and $4,000, and so on. I think I already gave you this answer, but how many terminal nodes does this tree have? That's right, it's 5. And so now I can calculate my root mean squared error on the test data. So I can pull out that testing data from my initial split, and I can predict my final model using this new test data. I can bind my columns from that test data so that I have both my truth and my predicted value, and I can look at that metric. And it shows me that the root mean squared error in the test is 363. Okay, so what I want you to do now is go ahead and start on this application exercise. I think this should take you about 10 minutes or so to do, but you can find the starter files if you go to GitHub and search for Apex 05 regression trees. And then I want you to pull that into RStudio and complete the exercises. Make sure that you're knitting, committing, and pushing frequently. But be sure to have final results pushed to GitHub by April 3rd at noon. And so this application exercise is going to be just like all the ones that we've done so far in class, where these are graded based on completion, not based on correctness. But make sure that you are pushing them to GitHub because as with our previous application exercises, this is how I am making sure that everyone's still participating in class. So it's good to be able to lecture you all this week. I hope that you have a good weekend and look forward to talking with you all on Tuesday. Bye.